Okay, welcome back. Um, in this video, we are going to talk about an application, face verification, which is different and sometimes easier than face recognition. And we will also discuss the Siamese network that are basically used for these kind of tasks. So the idea is the following. The face verification idea is the following. So let's say in the database or in your company or somewhere, you have certain authorized employees or persons, and and your camera now gets an image, and you want to recognize whether this image is the same as a particular person or not. Or in a nutshell, given two images, let's say image 1 and image 2, you want to know whether the two images are of the same person or not through the face data. So for example, consider this as a positive image, this as a positive image, positive in the sense that these two are similar. And let's say this is a negative image with respect to the positive image. So a network should be there that actually, given these two images, I1 and I2, give the dissimilarity really small. And given a positive and a negative image, it actually gives a large dissimilarity. And sometimes some networks, for example, convolutional neural networks, can be trained to give image I1 and I2 as pairs. And actually, the ConvNet actually learns the distance between I1 and I2, where this is some distance function. Let's say I'm assuming here a square distance, but any distance. And several times such a network is achieved in a way that you have a ConvNet and you pass it image 1 and the image 2 passed through the same ConvNet. So both image 1 and image 2, they actually share this ConvNet, and the results, the results, they are in a way that the distance between positive examples is minimum. And if a negative and a positive example is given, for example I1 and I3, the distance is really large. So it rather than generates a label, it actually learns the similarities between the positive examples and learns the dissimilarities between a positive and a negative example. And sometimes both the images that are given, they actually share the same parameters of a network, and such network is known as Siamese network. Also, there are several ways to formalize these kind of losses in these kind of examples. For example, one loss is known as a triplet loss, and the loss actually takes care of both similarity between positive and dissimilarity between positive and a negative. So the loss function actually minimizes this kind of distance. So this is minimized, and this is actually maximized. So positive and negative examples. So let's say this is weight alpha and this is weight beta. So what happens is if you have two positive examples and one positive and a negative example, the distance basically is maximized for positive and a negative, and distance is minimized for both positive examples. And the loss function actually receives an image, its positive variant or the similar image, and its negative variant, and these are basically three images, and that's why this loss is sometimes known as a triplet loss. So the requirement basically is to come up with a convolutional neural network that actually generate embeddings or generate the feature vectors. So for example, if I pass I1 in a network, it generates a feature vector, let's say F1. And if I pass I2 to the same network, it should generate the feature vector, let's say F2. And if I pass I3, it generates F3. And then what should happen is F1, which is the embedding or the feature vector after this whole convolutional pass-through, and this F2, they should be similar. These feature vectors should be similar. And F3 should be really dissimilar from both F1 and F2. And what happens is in these kind of applications, pre-trained models on face data sets are being used. And even one shot learning kind of scenarios are also achieved there. One shot learning is a paradigm in which you have, for example, you want to build a face recognition app, and you have only one image per class per person, or one can be replaced by a few short learning in which you have only a few examples for each category. And these kind of pre-trained models help in building such recognition system with very small amount of data per class, because they learn similarities rather than learning discrimination among different classes. So in this particular project, we are basically going to use um, and one more important thing, before actually recognizing faces, it is important to detect the face area from the image. So we detect the faces, we resize them in a same scale, and then we will be using a pre-trained model, and we will be getting embeddings from those, and we'll be getting the dissimilarities between embeddings. So we will be using MTCNN, convolutional neural network, for face detection, the face area cropping. And we will be using VGG phase 2, VGG phase 2 for as a pre-trained model in this particular project. So let's go to Jupyter Notebook in the next video and actually have a look into this example. Okay, in this video, we are going to actually implement face verification using VGGFace network. That is by DeepFace, VGGFace. Actually, we will be using version 2 of it, so VGGFace 2 model, as a network that will give us face embeddings. We will be using MTCNN network for face detection in the image, particularly cropping a face from the image. And so that's it. That's it. Basically, we will be using those, and they will, because this VGGFace 2 and MTCNN both, they require TensorFlow. So let's go to our command window and see what kind of packages do we really need. So first of all, we need TensorFlow, because VGGFace, Keras underscore VGGFace, that requires TensorFlow. In this my machine, the TensorFlow has already been installed, but let me tell you how to install TensorFlow. If you want to install that on a machine, it has already been installed on my machine, so requirements are already met. You can go to Google Colab and you can work there if you face any problems. Second, what we really need is MTCNN, so for face detection if the face area has not already been cropped out. So for that, pip install MTCNN. At my machine, this has been installed already, so requirements already met. Requirements, if you just read this, requirements already satisfied and requirements already satisfied. So it has already been installed. So then we need Keras VGGFace. So pip install Keras hyphen VGGFace. So that's the network that we'll be using, basically version 2 of it. At my machine, it has already been installed, so you're seeing that. Otherwise, it will download the package and install it for you. And next, we also use a dependency. For dependency, we also use Keras applications, so let's install those as well. Pip install Keras applications. So at my machine, of course, these things has already been installed, but these are the 4 things basically that you really need, other than Pillow and NumPy. So let's go to Jupyter and actually dive into sort out these things. So Jupyter Notebook, let's see. Yeah, so let me actually build a new Python file, and let me name that file as face verification, face underscore verification, let's say, that file. And just to increase the viewable area, let me hide that. And let's import the required packages that we really need. So import numpy as np, import pil. So from pil import image that might be needed for images. From mtcnn dot mtcnn import mtcnn, that's for face detection. From keras underscore VGG face dot VGG face import VGG face. And one more thing, we need preprocess input. So from keras underscore VGG face dot utils import preprocess underscore input. So I guess if everything is required. By the way, note here, TensorFlow as alone is not required here to import. I mean, you need not to import TensorFlow as TF. Rather, this VGGFace actually requires TensorFlow to be installed as a dependency. Further, the version I'm using of VGGFace version 2 actually requires TensorFlow 2.2 and above. At my machine, actually, the TensorFlow version is 2.3. Let me show you that import. Although we do not need it, but let me TensorFlow as TF, and let's say TF dot version. And at my machine, it is 2.3.0, which is the latest version. Anyways, so let's first import our model. So let's build certain things. Our detector is so our detector basically is the face detector is MTCNN. That's our detector. Let's make it loaded, and then we need basically the model VGGFace model. So let's build a model as well, because model VGGFace, and in this we have a lot of different variants. So let's use ResNet 50 architecture, ResNet 50, and then include top false. Do not include top. Just give me the feature extractor or embedding. As we also did the same kind of stuff in transfer learning module as well, where we do not actually include the top or fully connected layer. We just extracted the feature extraction layer. And input shape, most of these models, they have input shape 224 by 224 by 3, and this one also has the same shape. And then one thing that we do is we set the pooling type to be average. So pooling AVG. So that's our model. I have already basically already loaded that model earlier in my machine, so it will be quickly loaded. But if you first time load that model, it will download this model from internet, and it may take a while to actually load that model. But once loaded, it will load that model from the local copy. So now all set, we have our MTCNN, we have our VGGFace model. Let's load certain images and make the embeddings and do the stuff. So let's say we have, first of all, let's see where the images are located. So that's the directory. So let's download the positive image 1, Control C, and then we have here, so let's say P1, positive image 1, image dot open, and this is R. So that's the image, that's P1. P2 is the same image dot open with so this R for raw, and this we take positive image 2, let's say that's P2, and then we have a negative image as well. So P3 or N1, negative image N1, negative. image.open R, and we do that, and we have this -1. So these are the images. They are loaded already. If we see these images, for example, that's image 1, positive image 1. We can have positive image 2, that's positive image 2, and then we have negative image 1, which is this one. So as you can see, these are the 3 images. Now, first thing that we do is required for this empty CNN. We convert these images to NP arrays, because already the type of these images is pillow image type. So let's convert them to, so P1 again, np.as array, P1, P2, np.as array, P2, and then we have P3, which is np.as array. Oh, sorry, that's N1, not P3, N1. So that's it. Now let's write a function that actually extracts the face and returns the face image for us. So let's define f underscore get face, and it receives an image and returns a face. So let's write that function. That function first get the result of this detector. Remember, this D is our empty CNN detector. So that it actually get this image I, and then this actually give a tuple, or a tuple with a lot of details in that. So let's extract x1, y1, width and height of the image of the face area, and that is R0, and that is located in the attribute box. So let's get that. From there, we can now compute x2, y2 as x1 plus width and y1 plus height. So that x2. Now we are ready to extract the face area. So the face in this particular case, or let me call it as face, is basically I, y1 through y2 and x1 through x2. So that's our face. Let's return that face. And not only that, let's return that face in terms of rather than NP array, let's return that face in terms of the pillow image. So that we can plot that face just easily. So let's return the image dot from array, and that's the face. So let's return that. So now let's get the faces. So f1 is f get face p1, and f2, let's get face, that's p2, and f3 face is, let's say, or the first two faces are positive, the third face is negative. So get face n1, and these are now it will take a while to actually get these faces. Once the faces are available, and these are the warnings for how to actually boost up certain speeds and apply loops and stuff like so you, for now, you can ignore that, just for now. Let's see what is face 1. Face 1 is that's the face area, positive 1. Face 2, that's again the face area, and then we have this face 3, that's the face area. So now if you see earlier, we have the images, and now we have their face areas cropped. Not only that, it is good to actually resize all these faces in the standard form that is required by the network. So let's say for example, f1 equals to f1 dot resize, and let's say 224 by 224, that's the resize for f1. Similarly, F2 is F2 dot resize 224 by 224, and similarly we have F3 equals F3 dot resize, that is again 224 by 224 in tuple. So that's it. Now we can have, for example, F1 specializations. So that's the 224 by 224 size of F1. Next, what we do basically is we actually go and find out the embeddings, or you can say find out the feature vector for these kind of face images. But before that, it is good to basically pre-process it for the network that the network really requires. So for that, we first again convert these faces to face images to the NP arrays in the form of float 32. So let's say F1 is NP dot as array F1, and type may be float 32, and F2 NP dot as array F2 float 32, F3 NP dot as array F3 float 32. So after that, we are now ready to pre-process these inputs. So let's pre-process. F1 equals pre-process input F1, and the variant is 2 because we are using VGGFace variant 2. F2 is pre-process input, and we have F2 variant 2, and then we have F3, which is our negative phase right now, pre-process input, F3 variant 2. So this will actually pre-process the input in a way that is required by the model. And now we are ready to compute the feature vectors or embeddings. They call it embedding. So E1 embedding 1, or the feature vector, that is model dot predict. And so don't be confused with this predict function, because you might be thinking, what is it predicting? It is just generating a feature vector. But because the top layer is no longer there, the prediction actually results the value of the feature vector itself. One thing that you must notice, that although the shape of F1 is so let me first show you the shape of F1. So F1 dot shape is 224 by 224 by 3, and it turns out that the model actually requires the total number of images times the dimension of the image. So we need to reshape this image so that it looks like 1 by 224 by 224 by 3, and it can be done by np.new axis, no problem. So E1 embedding 1 is model dot predict, and here we give F1, and then we give np.new axis and dot keep all the rest of the dimensions. Embedding 2, that is also model dot predict F2 np.new axis, and then we have embedding 3, which is the embedding of a negative image. Embedding 3, let me call that as embedding of positive image, embedding of that, and then embedding of the negative image. So let me call that NE3. So model dot predict F3 np.new axis. So that will actually generate the feature vectors, and the hope is the embeddings for positive examples PE1 and PE2, they are closer to each other, and this NE3 is not closer to the positive one. So let's compute the distance metric just by square distances. Let's just compute the square distances. So distance between positives, so let me call it as positive distance between positives, that is PE1 minus PE2. By the way, before that, let me show you the shapes of these feature vectors. So the feature vector, this particular feature vector has 2048 dimensions, and similarly PE2 and NE3, all these. So these are the shapes. So these are eventually the feature vectors with feature vectors in or the feature points in 2048 dimensional feature space. So let's compute the positive distance positive, that is PE1 minus PE2, that's pointwise subtraction. Then we take squares, and then we actually compute the sum, np dot sum, and then we may compute a square root as well, 0.5 Euclidean distance, L2 distance, just for L2 norm. And then we compute the distance of a positive and a negative. Let me call it distance negative. np dot sum. Let's compute the distance from PE1 from NE3, and let's compute that square, and then let's compute that 0.5. Now the expectations are the positive distance should be smaller because that's the distance between the similar images, so that distance must be smaller, and this distance must be larger because that's the distance between a positive and a negative image. So let's see. And obviously if, running this on several images, we can learn a threshold after which we can say whether the two faces are similar or not. So let's just print distance positive, comma, distance negative. Let's just print those. And now you can see the positive distance between the positive examples is fairly smaller than the distance between a positive and a negative. And here you can learn a threshold to just verify that given two faces, whether the two faces are similar or not. And we have not built any model. We used actually the pre-trained model, VGGFace variant 2. You can have another model for that. And we just did it. And you can building upon this face verification, you can just transform this problem to face recognition for one shot learning as well, or few shot learning as well, in which in your company, for example, you have a few faces or very few examples per person. You can just convert this face verification problem to face recognition problem, no problem. And you can use the pre-trained models if that are available and really fast to actually upgrade. So that's about face verification. I hope you have enjoyed this.